Morning, students. Welcome to another session this morning. So today we are looking at learning outcome 4, which is develop understanding of linear modeling. Yesterday we looked at learning outcome 3, which is develop understanding of Bayesian statistics. And then we looked at the indicative contents, and then we had an explanation of Bayes theorem and how to use it in statistics, classification, and then probability basics, Bayesian classification, and then we looked at a good example, which is the play tennis example that we had yesterday, which play tennis training, and then we get the number of yes or no's, and the temperature and all, and the outlook. We also look at how to calculate it using Bayesian's theorem, among other things. So today, which is learning outcome 4, develop understanding of linear modeling. So what are the indicative contents? Simple linear regression, multivariable linear regression, linear least squares methods, ordinary least squares, weighted least squares, generalized least squares, and also cost function, gradient descent, forecasting, predictions. So as usual, we have a video to watch. So let me put the video up.
Meet Snowcat Cloud,
a
fully managed snow cloud data pipeline as a service. Now you can own your event data and advance your.
Hi.
We're watching this video after this session. So what is linear regression? Linear regression is a linear approximation of a causal relationship between two or more variables. So discuss simple and multiple linear regression models with example. So classification is a process of categorizing a set of data into classes. So you have set of data and they ask you about what's classification. This is literally like categorizing them into classes and not categorizing a given set of data into classes. The process starts with predicting the class of given data points. The classes are often referred to as targets, label, or categories. Assumption: feature values of the given instance are known. The set of possible classes is known and given. Classes are given as nominal values. For instance, classification of email messages, spam and not spam. So yeah, you have a data of email messages, and then you want to use classification. So that means that you have to categorize the email messages into spam or not spam. And also we have a popular example, which is news articles, which can be into classes of politics, sports, culture. We have email, spam or no spam, tumor, malignant or benign. So the output for binary classification, which is O or 1, true or false, O for negative class and 1 for positive class. So classification problem. Classification aims to divide items into 2 categories. The most common classification type is binary classification, where there are 2 categories, usually named positive and negative. So positive and negative, which is 0 or 1, true or false. If there are more than 2 categories, it is called multi-class classification. Classification problem cannot be solved by linear regression. Most commonly used classification algorithm is k-nearest neighbor, naive Bayes, decision trees, random forest, support vector machine. Logistic regression support both binary and multi-class classifications problems. So we have the classification algorithm. So this is the algorithm, literally what we mentioned in the previous slide. So we have the naive, or I think it should be naive or naive Bayes, and then we have artificial neural network, logistic regression, decision tree, k-nearest neighbor, support vector machine, stochastic gradient descent, and random forest. So let's we have a good example of this here. I think we have to log in or something. Yeah. So I'm not sure if we have to access, log in or do something. So yeah, here we have it. So this article explains what class naive-Bayes classifier is and all. So I think I think you have to log in to you have access to it. Let's look at So what does naive-Bayes classifier means? A naive-Bayes classifier, a family of algorithms based on Bayes theorem. That's why I think it's naive or naive. I don't know. Assumption of feature independence. These classifiers are widely utilized for their simplicity and efficiency in machine learning. The article delves into implementation and application, shedding light on their and practical blah 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 blah. So what is naive-Bayes classifiers? Naive-Bayes classifiers are a collection of classification algorithms based on Bayes theorem. It is not a single algorithm, but a family of algorithms where all of them share a common principle. That is, every pair features being classified is independent of each other. So that's actually what it means. To start with, let's consider a data set. So that's what it means. So what is binary and multi-classification? Based on the number of classes, classification can be binary. Instances should be classified into two classes. That is 0 or 1 positive or negative. Multi-class, more than two classes are used for classifying instances. In both cases, the classifier works in a rather similar manner. In multi-class classification, the classifier learns iteratively so that in each iteration, it learns to differentiate instances of one class from the other instances. Give us a sec. Yeah. So we have multi-class classification, which we can also check. So this website says that multi-class classification is the process of assigning entities with more than two classes. Each entity is assigned to one class without any overlap. An example of multi-class classification using images of vegetables, where each image is either carrot, tomato, or zucchini. Each image is placed in one of the three classes. So because it is multi-class, so it has more than one. For example, one image cannot be both a carrot and a zucchini. So yeah. So that's it. And also this website explain what naive-Bayes is, and then advantages of it, k-nearest neighbor, so and decision trees. So yeah, it also have differences between binary versus multi-class classification. So yeah, like we said, example of binary classification include image spam detection and so on. So how is multi-class classification used? Multi-class classification has a variety of applications. It can be used to identify animals from images and sort them into categories. Give us a sec. Yeah. So multi-class classification have a variety of applications. It can be used to identify animals from images and sort them into categories. Cybersecurity companies can use multi-class classification to sort incoming emails as spam or not. It can also be used when analyzing an individual mood into more than positive or negative. Instead, we use multiple categories, such as happy, sad, depressed, excited, etc. There's no limit to the amount of classes used in multi-class classification. That is why it is called multi-class classification. So let's move on. Yeah, so this is it. We have the class 1, class 2, and class 3. So we have the iteration 1, iteration 2, and iteration 3. This is the flow. So what is multi-label versus multi-classification? We have binary classification, but multi-class classification and multi-label classification. This table shows the binary classification, and the table 2 shows the multi-class classification, and table 3 shows multi-label classification. As you can see, in the y-axis, there are many labels to it. So discuss various linear least squares methods with examples. This is the new subtopic. Following health parameters are monitored for a number of peoples. Each person contains following information: pregnancies, glucose, blood pressure, skin thickness, insulin, BMI, age. The output for binary classification Y, which is 0, 1, 0 for negative class and 1 for positive class. So what is the problem? Given the values of all these attributes, classify whether a person has diabetes or not. So yeah. Yeah, so that should be glucose. So we can do this, which is pregnancy is 6, 148, and the blood pressure, the insulin is 0, and then the age is 50. So the outcome is 1. So which is 1, 0. So because the insulin is 0, 0, and 0 share, and then skin thickness is 0. So this is the outcome, which is 1, 0, 1, 0, which is positive, negative, positive, negative, positive. That's what that means right there. So performance measure, the most frequently used metrics, confusion matrix, accuracy, precision, and recall, F measure, area under ROC curve. So we have confusion matrix. This serves as the basis for calculating other performance measures. So we have the actual class, a predicted class. We have yes, no, and then TP means true positive, FP means false positive, TM means true negative, FN means false negative. So accuracy is the percentage of correctly classified instances. Accuracy is TP plus TN divided by N, where TP is true positive, TN is true negative, and N is the total number of instances in the data set. This is self-explanatory. What is accuracy? Because right here we have accuracy, precision, and among other things. So what is accuracy? Accuracy is one metric for evaluating classification modules. Informally, accuracy is the fraction of predictions our model got right. Formally, accuracy has the following definition. Accuracy is number of correct predictions divided by the total number of predictions. So take, for example, you've got you have like 10 predictions, and then you predict 6, right? So accuracy is number of correct predictions, which is 6, divided by total number of predictions. Accuracy alone doesn't tell the full story. Where you are working with a class imbalance data set like this one, where there's a significant disparity between the number of positives and negative labels. So yeah, let's try calculating accuracy for the following model that classify 100 tumor as malignant, the positive class, or benign, which is the negative class. So we have test positive, like we saw here, TP, TP, FN, FP, TN. So we have here TP, which is true positive, reality, malignant, which is positive, model predictive malignant, number of TP results is 1, and then the false positive, reality benign, which is negative, model predicted malignant, number of false positive results is 1, and then for this, we have false negative, FN, reality, which is malignant, which is positive again. So ML model predicted is benign, which is number of false negative is 8, and then the last one, true negative, TN, reality is benign. My bad. Reality is benign, the negative, which ML model predicted benign, number of TN results is 90, and then the accuracy is TP plus TN, like we saw here, number of correct predictions. So which is TP plus TN, true positive, true negative. That is 90 plus 1, and then divided by the total number of prediction, which is this, and this, which is TP is 1, TN is 90 plus FP plus FN. That is 91 divided by 92 and 90. I think that should be 99 or something like that. This is 8, 10. That's 100. So that is 91 divided by 100. That's 0.91. So that is literally what we have right there. Our next slide is precision and recall. Precision is defined as is the accuracy of its positive predictions. Out of predictive positive, how many were actually positive? Precision is TP. Predicted positive is equal to. So yeah. So we have TP divided by TP plus FP, which is false positive, true positive, and null. Example, out of all the messages marked as spam, the percentages of those that are really spam messages. Recall, so recall is the model's accuracy on the actual positive class. How many actual positive did the model identify? And then we have the formula for recall, which is TP divided by TP plus FN, which is false negative. So instead of using false positive, use false negative. Example, out of all the messages that are really spam, this percentage of those that have been detected or classified as spam. So we have precision and recall. So precision is equal to true positive divided by actual results, which can also be true positive divided by true positive plus false positive. So that is the formula. And then we have recall, which is true positive divided by predicted results, or true positive divided by true positive plus false negative. And then we know accuracy is the true positive plus true negative divided by total. So that is what that is. We can see the accuracy literally right here. So we have the true positive and then true negative because it is true. So yeah. Continuation, precision versus recall. In practice, one always needs to make a compromise between these two metrics. By increasing recall, we decrease, though unwillingly, precision and vice versa. And then this is the chart. Under ROC curve, which AUC, ROC curve is used for visual comparison of classification models, which shows the trade-off between the true positive rates and the false positive rates. The area under the ROC curve is a measure of the accuracy of the model. It is used for measuring performance of binary classifiers. It takes values from 0 to 1 interval. The case of random classification, AUC is equal to 0.5. So as the AUC value is greater than 0.5, the classifier is better. 0.7 minus 2, 0.8 is considered fair. 0.8 to 0.9 is considered good. And anything greater than 0.9 is excellent. And then we have it right here. area under the ROC curve with the sensitivity or true, and then every other thing. Yeah. Moving on. Steps for classification training. So this is the flow chart and the steps and everything. So we have the training data with feature selection, we pre-process it, and then we train it with that's training labels, learn model. And then we also have testing data with the features, the learn model, the prediction, and then SVM neural networks. This is literally what we use to train it. SVM neural networks, naive-Bayes, Bayesian network, logistics regression, randomized forest, k nearest neighbor, etc. So our next topic is fold cross validation for training and testing. Split data into three subsets. A training set to build our model. Give me a second. Yeah, sorry about that. Split data into three subsets. A training set to build our model, 60 to 80% of the data set. A validation set to compare the performance of our model using different parameters for our algorithm of choice, 10 to 20% of the data set. A test set that has not been used in creating the model, 10 to 20% of the data set. Use precision lookup to test the model accuracy. So we have logistic. Our next topic is logistic regression. So what is logistic regression? Logistic regression is a popular statistical model used for binary classification. However, it's used for multi-class classification and based on concept of probability. Logistic regression describes and estimates the relationship between one dependent binary variable and independent variables. It is a special case of linear regression where the target variable is categorical in nature. The outcome of target variable is dichotomous in nature. Linear regression gives you a continuous output, but logistic regression provides a constant output. An example of the continuous output is a house price and stock price. Example of discrete output is predicting whether a patient has cancer or not, predicting whether the customer will churn. So this is it. We have the logistic regression and we have the linear regression. My bad. Linear regression is here, and then the logistic regression is the one on the right. So cost function used in logistic regression, sigmoid function. So the sigmoid function, aka logistic function, given as S-shaped curve that can take any real value number and map it into a value between 0 and 1. We set a threshold value above which we classify value into class 1, and if value goes below the threshold, then we classify it in class 2. If the output of the sigmoid function is more than 0.5, we can classify the outcome as 1 or yes. If it is less than 0.5, we can classify it as 0 or no. If the output is 0.5, we can say in terms of probability that as there's 75% chance that the patient will suffer from cancer. For example, for example, if we are modeling people's sex as male or female from their height, then the first class could be male. And the logistic regression model can be written as a probability of male given a person's height or more formally. So we have the P, sex, male, height, and then we have this curve which is S-shaped. Logistic regression continued again. In logistic regression, we learn the conditional distribution. And then let P be our estimate of P, where W is a vector of adjustable parameters, assuming there are two classes, y is equal to O and y is equal to 1. Constructing a learning algorithm. The conditional data likelihood is the probability of the observed y values in the training data. Conditions on their corresponding x values, we choose parameters W that satisfy W as max. And then this is the formula where W is equal to this, which is the vector of parameters to be estimated. Y denotes the observed value of Y in the TH training example, and X denote the observed value of X in the TH training example. Steps for logistic regression. Step 1, we determine the best fitted line by following the linear regression hypothesis. That's the formula. Step 2, thus, the predicted value from the linear regression gets converted into probability by feeding into the sigmoid function. Step 3, if the probability of a particular element is higher than the probability threshold, then we classify that element in one group or vice versa. So, example of logistic regression by stochastic gradient descent. So that is it. Yeah. For this data set, the logistic regression has 3 coefficients, just like linear regression, for example. The formula which is BO plus B1 times X1 plus B2 times 2. We'll first determine the value of BO, B1, and B2 using gradient descent, assuming rates alpha is 0 to 1. Initial values of BO is equal to B1 is equal to B2 is equal to 0. Given each instance, calculate a prediction using the current values of the coefficient. Calculate new coefficient values based on the error in the prediction. We continue to update the model for training instances and correcting errors until the model is accurate enough or cannot be made any more accurate. So that's the continuation. So the first training instance is X1, which is 2.78, which is this. And then X2 is that, which is this. YO is equal to 0, BO is equal to P1, B2 is equal to 0. So the prediction formula is this, which is 0.5. So how do we calculate this? Calculate the new coefficient value using a simple update equation, which is B is equal to B plus alpha, Y minus prediction, 1 minus prediction times X. Assume alpha is equal to 0.3, B is bias and half, and input X 1 new. So this is the formula and also BO, B1, and B2. Yeah. So yeah, can repeat the process, you can repeat this process and update the model for each training instance in the data set. The coefficient calculated after 10 epochs of stochastic gradient descent are BO is equal to that negative 0.4, and B1 is 0.8, and B2 is negative 1.1. So prediction of the class using sigmoid. Once we know the value of BO, B1, B2, we use it to determine predicted value for our given data set through sigmoid calculation. Calculation is shown below. Let me see if I can zoom this in. Yeah, so that table that we have there, this is the calculation. So critically evaluate how linear regression models are used in AI machine learning. Difference between logistics and linear regression. Linear regression is used to handle regression problems, whereas logistic regression is used to handle the classification problems. Linear regression provides a continuous output, but logistic regression provides discrete output. The purpose of linear regression is to find the best fitted line, while logistic regression is one step ahead and fitting the line values to the sigma curve. The method for calculating loss function in linear regression is the mean squared error, whereas for logistic regression, it is maximum likelihood estimation. So types of logistic regression, we have the binary logistic regression, multinomial logistic regression, and ordinal logistic regression. So what is binary logistic regression? The target variable has only two possible outcomes, such as spam or no spam, cancer or no cancer. That is yes or no, 0 or 1, true or false. Multinomial logistic regression, the target variable has 2, 3 or more nominal categories. So we've been talking about this. Binary is 0, binary is 1, and multinomial can have many, 3 or more, such as predicting the type of wine. Ordinal logistic regression, the target variable has 3 or more ordinal categories, such as restaurants or product rating from 1 to 5. The drawback in logistic regression, if the number of observations is lesser than the number of features, logistic regression should not be used. Otherwise, it may lead to overfitting. It constructs linear boundaries. The major limitation of logistic regression is the assumption of linearity between the dependent variable and the independent variable. It can only be used to predict discrete functions. Hence, the dependent variable of logistic regression is bound to the discrete number set. Logistic regression requires average or no multicollinearity between dependent variables. It is tough to obtain complex relationships using logistic regression. That brings the end to our session for today, and then these are references. Forget to send us an email if you have questions and all. So yeah, just for recap, or let's just watch the video first. Then we have a recap.
It is time for the actual introduction of regressions. Let's start with some dry theory. A linear regression is a linear approximation of a causal relationship between two or more variables. Regressions models are highly valuable as they are one of the most common ways to make inferences and predictions. The process goes like this. You get sample data, come up with a model that explains the data, and then make predictions for the whole population based on the model you have developed. There is a dependent variable labeled y being predicted and an independent variable labeled x1, x2, and so forth. These are the predictors. Y is a function of the x variables, and the regression model is a linear approximation of this function. The easiest regression model is the simple linear regression. Y is equal to beta 0 plus beta 1 times x plus epsilon. Let's see what these values mean. Y is the variable we are trying to predict and is called the dependent variable. X is the independent variable. When using regression analysis, we want to predict the value of y, provided we have the value of x. But to have a regression, y must depend on x in some causal way. Whenever there is a change in x, such change must translate into a change in y. Think about the following equation. The income a person receives depends on the number of years of education that person has received. The dependent variable is income, while the independent variable is the years of education. There is a causal relationship between the two. The more education you get, the higher income you are likely to receive. This relationship is so trivial that it is probably the reason you are watching this course right now. You want to get a higher income, so you are increasing your education. Now, let's pause for a second and think about the reverse relationship. What if education depends on income? This would mean the higher your income, the more years you spend educating yourself. Putting high tuition fees aside, wealthier individuals don't spend more years in school, and high school and college take the same number of years, no matter your tax bracket. Therefore, a causal relationship like this one is faulty, if not plain wrong. Hence, it is unfit for regression analysis. Let's go back to the original example. Income is a function of education. The more years you study, the higher income you will receive. This sounds about right. All right. What we haven't mentioned so far is that in our model, there are coefficients. Beta 1 is the coefficient that stands before the independent variable. It quantifies the effect of education on income. If beta 1 is 50, then for each additional year of education, your income would grow by $50. In the USA, the number is much bigger, somewhere around $3,000 to $5,000. So, for each additional year you spend on education, your yearly income is expected to rise by $3,000 to $5,000. And that's not considering higher education or tailored courses, like this one. The other two components are the constant beta 0 and the error, epsilon. In this example, you can think of the constant beta 0 as the minimum wage. No matter your education, if you have a job, you will get the minimum wage. This is a guaranteed amount. So, if you never went to school and plug in an education value of 0 years in the formula, the regression will predict that your income will be the minimum wage. Makes sense, right? The last term is epsilon. This represents the error of estimation. The error is the actual difference between the observed income and the income the regression predicted. On average, across all observations, the error is 0. If you earn more than what the regression has predicted, then someone earns less than what the regression has predicted. Everything evens out. All right, the original formula was written with Greek letters. What does this tell us? It was the population formula. But we know statistics is all about sample data. In practice, we use the linear regression equation. It is simply y hat equals b0 plus b1 times x. You heard it right. The y here is referred to as y hat. Whenever we have a hat symbol, it is an estimated or a predicted value. b0 is the estimate of the regression constant beta 0, while b1 is the estimate of beta 1, and x is the sample data for the independent variable.
For more videos like this one, please subscribe.
So that brings the end to our session for today. So let's have a recap of what we spoke about. Yeah, so today we looked at developed understanding of linear modeling, and then these are the indicative contents: simple linear regression, multivariable linear regression, linear least squares methods, ordinary least square method, weighted least squares, generalized least squares, cost function, graded descent, forecasting, and prediction. So this brings the end to our session for today. Next week is the assignment session. So I'll see you next week. Bye.